convert 95% to a decimal, then we take our percentage symbol, move it two places to the left, and we have 0.95. So that's our decimal. If we take 1 minus 0.95, we are left with an alpha level of 0.05. We could do the same thing with an alpha level where we want to determine for, instead of 95%, let's say 99%. We can plug in the same formula. 1 minus 0.99 leaves us with an alpha level of 0.01. So that's the relationship between level of confidence and or alpha level. Okay, level of confidence and alpha level. 95% confidence is connected to an alpha of 0.05. 99% confidence connected to an alpha of 0.01. The reason that those are relevant is because, remember, when we're talking about 95% being attached to a z-score of 1.96, that's because we learned, and we could look this up if we wanted to, the reality is that 95% of the population is going to exist between 1.96 standard deviations above the mean and 1.96 standard deviations below the mean. 95% of the population exists within this area. The remaining 5%, because if you think back to being introduced to characteristics of the normal distribution, 100% of cases fall under the normal curve. So the difference between 95% and 100% is 5%. So that 5% exists beyond each side of our z-scores. It gets split in half. We're working with two tails. We're not only working with one tail. So that 5% gets cut in half. Half of 5% is 2.5%. So it'd be 2.5% on the right tail and 2.5% on the left tail. And we're effectively saying there is a 2.5% chance that we are going to calculate a sample mean that is significant, right? On either the right side or the left side. 2.5% is really, really low. And that's kind of the point. It should be low. Because if we're trying to compare our sample to our population and determine whether or not there's a significant difference between them, we don't want to leave it open to, a really high likelihood that we could calculate a sample mean far from the population. We don't want to say there's a 50% chance. It's a 1 out of 2 chance that we're going to get a sample mean far from the population. We want to really increase the I guess decrease would be the more appropriate way to think about it. We want to decrease the likelihood that we are going to get a sample mean in the significant area so that we can say with confidence that, we're 95% confident that something about our analysis is accurate, okay? All right, so I'm going to go ahead and clear off all my markings there, and let's go ahead and get back to this. So these shaded areas in the tails are called the critical region. So this is still a part of step 2. The critical region is the area of the normal distribution where sample means are extremely unlikely to occur. Our alpha level defines the boundaries for the critical region. In the previous slide, I showed you that example, but this illustration here does the same thing. So we have 1.96 serving as our boundaries for the critical region. And the critical region then becomes the extreme 5%. Notice that it says extreme 5%. It's also pointing to both sides of our normal distribution. And remember, it's 2.5% over on the left side in the left tail, 2.5% in the right tail. The boundaries of the critical region separate the extremely unlikely sample means from the likely sample means. All right. Okay. So as far as an example, I've provided one here. I decided to give you the examples earlier, 2 slides ago, but this information here effectively communicates the same ideas. Let's say we select an alpha level of 0.05. Remember that alpha levels reflect a low level probability. Since our alpha level is a measure of probability, we can convert the decimal of 0.05 to a percentage of 5%. As researchers, that effectively means that we are trying to find a sample mean that only has a 5% chance of occurring. Also remember that we convert sample means to z-scores in order to compare across distributions. With a 5% chance of occurring, we need to find a sample mean that has a z-score that is less than negative 1.96 or larger than 1.96. It is only within these areas, in these critical regions, that we can say there's a significant difference between the sample mean and the population. So this is all a part of step 2. Step 3 is to collect data and calculate sample statistics. This is a very quick kind of component, largely because we're not actively collecting data in this particular class right now. So it's in step 3 that we will go out, we will collect our sample data, and we will calculate our sample mean. The goal is, as you've recognized through this presentation, to compare our sample mean against the hypothesized population mean. There are ways to determine a hypothesized population mean, but it goes a little bit beyond the scope of this class. For our practice, I will show you, where relevant, I will provide hypothesized population means. And so, know that in future classes that you take, you'll learn more about how it is that you come to the conclusion of what a hypothesized population mean is for your particular research. So this comparison between the sample mean and the population mean is made by calculating a z-score. Finally, in step 4, you make a decision. I know it sounds odd for me to say to you, you make the decision, but it's a decision based on the analysis that you conduct. So the z-score is calculated in step 3, and it's used to determine whether there is significant, if there is not significance, or if there is significance. That means there are 2 possible outcomes. The first possible outcome is that we retain the null hypothesis. If you retain the null hypothesis, this suggests that your sample mean was close to the population mean, so there's no significant difference between them. Or you reject the null hypothesis. If you reject the null hypothesis, this suggests that your sample mean was far from the population mean in a critical region, so there's a significant difference between the two. Okay? I do like to incorporate this in here because it's possible you can come across this language later, but it's important to note that this language of retain the null hypothesis, at times you can actually see this referred to as fail to reject the null hypothesis. I just want you to know that it means the same thing. Fail to reject the null hypothesis or retain the null hypothesis both describe the same outcome, that there is no significance. Okay, so type 1 and type 2 errors. Errors in decision making, effectively. So uncertainty in hypothesis testing. The reason hypothesis testing is inferential is because we're using limited information, because we're drawing a sample to reach a general conclusion about a larger population. It's possible to come to an incorrect conclusion in our analysis. These 2 types of error are type 1 and type 2 error. Type 1 error occurs when a researcher rejects a null hypothesis that is true. To kind of put this into a bit of an example, let's say I'm running my analysis on how many hours are needed in order to score higher than 80%. And let's say I come to the conclusion through my analysis that 5 hours of studying results in a higher score than the average. If I come to that conclusion, I say, yeah, there's a significant difference between students who study for 5 hours versus those who study for 3 hours, and I put that out into the world, then people are going to say, wow, this is amazing research. We want to make sure we get our students to study for 5 hours. What if I made a mistake, though? If I made a mistake and people are out here studying for 5 hours and they're not seeing those results, that's because I came to a conclusion that was in fact not correct. I concluded that my research found a significant difference, but in reality, there's no significant difference. Okay? So that's a type 1 error. A type 2 error is when a researcher retains a null hypothesis that is false. So, in this example, still applying the same example rather, let's say I'm the researcher, I'm collecting my data, and I studied people who studied for 5 hours, and if I came to the conclusion that people who studied for 5 hours, they actually got a mean, a sample mean that was pretty close to the population mean, there's not really a difference. And I say, oh, well, studying for 5 hours doesn't seem to make a difference. And I'm wrong, then that's when I'm committing a type 2 error. Okay. So in a type 2, I'm retaining a null hypothesis. I'm saying there's no significance between the sample mean or significant difference between the sample mean and population mean, but that's incorrect. Okay. So how do we reduce the likelihood of making a mistake? As you can imagine, as researchers, we definitely want to reduce the likelihood of making these mistakes. As researchers, we want to reduce the likelihood of making a mistake. One way to affect the likelihood of making a type 1 error is through the alpha level. The alpha level, which we learned is the probability of getting a z-score in a critical region, also tells us the probability that the test will result in a type 1 error. The smaller the alpha level, the less likely of us making a type 1 error. It is impossible, however, to determine an exact probability associated of making a type 2 error, so we don't necessarily have a probability associated with that. You might be thinking to yourself then, okay, well, if selecting a smaller alpha level reduces the likelihood of making a type 1 error, then wouldn't I just always lean on choosing a lower alpha level? The logic I understand. However, there are some considerations that we have to make as researchers. The alpha level serves two functions. Firstly, determining the boundaries for the critical region by defining extremely unlikely outcomes, right? That's one of the functions of the alpha level. The other function is determining the probability of making a type 1 error. Your primary goal should be reducing the likelihood of making a type 1 error. However, the smaller the alpha level, the more evidence you need to prove your results. Alpha levels of 0.05, 0.01, and 0.001 balance the risk of error with the demands of research results. In a previous example, I shared with you how if we're using 95% confidence, we have an alpha level of 0.05, that a sample mean of 2.15 was considered significant if we were working with an alpha level of 0.05. But when we changed our alpha level to 0.01 and now our critical regions are at 2.58, then that same sample mean of 2.15 is no longer significant. It sounds good at face value, but you are then requiring that the results of your research show even more evidence of significant difference. And you have to kind of weigh out as a researcher what makes the most sense for the kind of research that you're conducting. So the above alpha levels of 0.05, 0.01, and 0.001 all correspond with confidence levels of 95%, 99%, and 99.99% confidence. However, just to reiterate, 95 and 99% are the most common.